Okay, please.
So it's a kind of introduction. As you know, I'm not an expert of modeling. I'm much more a kind of experimental guy. So that's why I'm not always so efficient for such kind of things. So first of all, I would like to thank the Professor Siebertine who invited me to present these results that we obtained at Cosmetic Europe. So the talk is not focused on modeling on formula, but how we can use modeling in a different context. It's really the context of in silico skin penetration. So I don't know if you know, but for the cosmetic industry, animal testing is banned for any kind of reason. That means that when we have in mind to predict the risk associated to topical exposure, we have to consider two different things. So I use the example of the lion. We all agree that the lion is quite dangerous. I'm at home today, and I'm sure that even if a lion is dangerous, I have no risk to with the lion because I'm not able to meet a lion. However, if I want to go tomorrow to the circus or zoo and to enter in the park where is located the lion, of course, I will increase dramatically the exposure and I will take risk. It's the same thing for the cosmetics or any kind of chemicals, that the hazard is evaluated based on the properties of the chemical, and this hazard has to be combined with the exposure to perform the risk assessment. The exposure is also a product of two different components, the condition of use and the bioavailability. The HADME task force was created, I think it's 10 years ago, and led by Andreas Schepke from Bayersdorf and Nikki Witt from Cosmetic Europe to address this question. How we can refine the skin bioavailability to improve the risk assessment. The skin is the main route of exposure to cosmetic, and it's a very efficient barrier. That's the main function. One of the main functions of the skin is to prevent the absorption of chemicals. And of course, the idea is to perform the evaluation in as close as possible to the real condition of use. So I use the term of skin bioavailability, but what do we have in mind when we are talking about skin or cutaneous bioavailability? It's the sum of different components. The first one is the chemical is enter into the skin, and especially with the stratum corneum, which is the main limiting step for the skin. Then when it's entered into the skin and reach a variable part of the skin, it can be metabolized into different kind of chemicals. And then it's distributed in different skin layers and eliminated from the skin into the blood circulation, where other kind of aspects are effective, in meaning metabolism by the liver, distribution in the body, and eliminated by the kidney. So and all of these components are is the sum of these components reflects the bioavailability. So as you can see, the bioavailability is a quite complex process, and the aim of the task force and the goal was to evaluate the different factors affecting the skin bioavailability related to local toxicity. When we say local toxicity, is mainly about tolerance and sensitization, or for systemic toxicity. For such purpose, we would like to provide suitable data for different components of the skin bioavailability using a large set of chemical with appropriate protocol. And ultimately, the idea was to use such kind of data to develop and optimize in silico model dedicated to skin absorption. For such purpose, the first thing was to select a set of chemicals, and we worked on a set of 50 chemicals that includes a large chemical space in terms of molecular weight and log P. We have some constraints. The constraints are based on the physico-chemical properties. So first of all, we would like to prevent very highly volatile chemical. we would like to have some chemicals which are enough soluble in water, and due to the different kind of protocol that we use, we would like to have radio labeling chemicals. So at the end, we define a set of 50 chemicals, and we run several different assays, set solubility of the different chemicals in different solvents. We measured also the ability of chemical to react with the proteins, knowing that this aspect is one of the key events for sensitization. We measured also the partition and diffusion coefficient of the chemical in different skin layers. Skin metabolism was also evaluated through 2 different approaches, with skin, ex vivo human skin, and also on subcellular fraction. And at the end, we measured the skin distribution of the 50 chemicals in a standardized protocol. All of these results were published with the list of the reference reported here. Here is the classical skin distribution protocol. So I don't know if you're familiar with such kind of protocol, but let me explain how we do that. For such kind of study, we are using human skin, abdominal human skin coming from plastic surgery. The skin is set up on French cells that define an exposure area, and it's made of different kind of components. You have the skin, you have a cap which defines the exposure area, and the receptor compartment is filled with the receptor fluid mimicking the blood circulation. The skin is well controlled and so on in terms of characterization, in terms of integrity, temperature, and so on. Then we applied a given volume of the solution, 10 microliters per centimeter square. Then after 24 hours, the skin is washed to remove all of the chemical remaining at the skin surface. Then the different skin layers is separated. For the stratum corneum, it's obtained by tape stripping, meaning successive different tapes. The epidermis and dermis separated by heating, and then all of these samples are extracted, and the amount of chemical was determined by scintillating content. Here is it, and so this protocol is compliant with the OECD guidelines. Here are the typical results that we obtain. So I reported one of the results for cinnamaldehyde, for example, and we determined the fraction of the chemical found in the different skin compartment, meaning it was the chemical remaining at the skin surface, stratum, epidermis, dermis, and receptor fluid. And we also provide the kinetic of the penetration of the chemical through the skin. So that's all of the sets of the data that we have. Then the idea was to use, okay, what is the performance of the actual in silico model to predict the skin penetration? We work on a subset of 25 chemicals. We evaluate 6 different models listed here. For all of the evaluation was done by some person having some enough experience with each model, and to all of the people we provide the same set of data, including chemical name, physical chemical properties, partition and diffusion coefficient measured in the stratum corneum, and the condition of the exposure, meaning vehicle, pH, skin thickness, and the mass balance. The mass balance is the sum of the amount of chemical found in the different compartments normalized to the amount applied initially. So I just precise the condition of the exposure. It was finite dose of vehicle, meaning 10 microliters per centimeter square, which is a small droplet. 24 chemicals were solubilized in water, and 4 chemicals were solubilized in ethanol. So over the 6 models, one was discarded because the model was able to predict only the permeability coefficient. And we were interested by the amount of chemicals that is able to enter the skin and to reach the viable part of the skin, meaning the epidermis, dermis, and receptor free. So all of the rest of the evolution was done only on 5 different models. The first thing is the effect of the evaporation. Here, the graph reports the mass balance. I just remind that the mass balance is the sum of the amount of chemical found in the different skin layers normalized to the theoretical amount, to the applied amount. And everything, if everything is fine, normally the mass balance should be at 100%. You should not lose chemical whatever. Here, in that case, when we plot the mass balance as a function of the vapor pressure, we can see that after a given value for the vapor pressure around 0.01 millimeter de mercury. Sorry, I don't know the words for mercury in English. So we can see that for such kind of chemical having high volatility, the mass balance decreased. That is related to the volatility of the chemical. Of course, a part of the chemical can be lost simply because it evaporates over the time. So the idea was to know at the first intention if the models are able or not to predict the chemical volatility. Over the 5 different models, 3 models were able to predict the chemical evaporation, and here it's reported the predicted evaporation as a function of the estimated evaporation. And the estimated evaporation was the difference between the mass balance at 100%. As you can see, more or less the model are able to discriminate between non-volatile chemicals, which are reported here compared to the very highly volatile chemicals, but the correlation was not so good. Then the other things. I just remind that when I said at the beginning that the skin, the main component of the skin that limiting the skin absorption is the stratum corneum coefficient. Sorry. It's the stratum corneum. And the stratum corneum is characterized by 2 different parameters, which are the partition coefficient and diffusion coefficient. We have 2 ways. It can be predicted with some models, and all models involved have some model to predict the partition and diffusion coefficient, or it was also measured, and that's one of the papers that we published. Here, for one model, we saw the impact of the difference between predicted and measured partition and diffusion coefficient. It was a SimSip model, and we can see that for this model, we improve the overall correlation. Nevertheless, it cannot be seen as the general rules, because here are the reported the coefficient correlation for the different models, and depending on the models, sometimes it don't change, it doesn't improve the correlation as for the Surrey model, and for some others, that it could be better to use predicted rather than measured coefficient. The reason for that is that the protocol used to measure this partition and diffusion coefficient was done, I reported the experimental condition, it was done in infinite dose, meaning a large volume of vehicle. That could explain why it's not the measured partition and diffusion coefficient cannot always improve the performance of the model. That's one of the key points, is that meaning that we have to use a protocol which is compliant with the experimental condition. Here is reported the list of the different, the results of the different models to predict dermal delivery.
Sebastian, could you please talk in front of the microphone, because I think when you move your head, then your voice disappears. All right.
Sorry. So I said so here's the results that we obtained for the 5 different models, and we predict the dermal delivery, meaning the amount in the variable part of the skin. The gray correspond to volatile chemicals, the black correspond to non-volatile chemicals. And as you can see, some of the model were more or less performant, and one of the most appropriate model was the model TCAT from Simulation Plus. I just precise that this evaluation was on date. And of course, if we perform again this simulation with the new version of each model, I cannot guarantee that the result is the same. Here, because I just remind that also that we are also interested by the how the chemical is distributed into the skin, and that could be of interest, especially for the local tolerance, as the local toxicity, sorry, as a local tolerance or skin sensitization. As you can see, if more or less the model, some models are the ratio between predicted and measured value are more or less close to 1. As you can see in the different skin layers, it can be really, really worse. The TCAT model, which provides the best correlation for the dermal delivery, shown the amount in dermis is largely overestimate, whereas the amount in stratum corneum is largely underestimate, and the amount in epidermis is, well, the mean is around 1, but it's the individual value are spread quite largely over this mean value. So none of the models are able to predict accurately with good precision the amount in the different skin layers. So I heard the previous presentation. Of course, it's not emulsion, so it's a kind of simple aqueous solution. So anyway, we evaluated in our study not a complex formula, but we also compare simply water and ethanol. We know that normally ethanol acts as a chemical enhancer and should promote the absorption of the chemical in and through the skin. But as you can see here, in black corresponding to the experimental value for the aqueous solution, and here in dotted bar correspond to the value with ethanol. For the three tested chemicals, with ethanol, the skin absorption decreased. It is really related to the fact that we are applying at finite dose, finite amount of vehicle was applied, and the ethanol should evaporate before entering into the skin and affecting the barrier function of the skin. All of the models shown great difference between all of the models predict lower dermal delivery with ethanol, but with some huge differences. For example, for the CDC model, for the geraniol, it predicts lower dermal delivery, but with a lower impact compared to the experimental value. Whereas for the parabens, the model predicts much more lower absorption with ethanol compared to the experimental value. So that just means that for simple vehicles such as ethanol, the models are not so well, any models are not so well effective to predict clearly the behavior of the formula. I just remind the conclusion of this first evaluation. First of all, the skin metabolism was not taken into account in this study. The chemical volatility should be considered in the model, and now it's integrated in the TCAT model. The dermal delivery, meaning the amount in the variable part of the skin, is more or less well predicted only for a PBS solution. And the other thing is that we have a subset of 25 other chemicals. And when we evaluate these additional 25 chemicals with the TCAT model, the performance was worse. And one of the reasons that this second set of chemicals concern include also reactive chemicals. And I said at the end that there is lack of performance to predict the effect of the solvent. So that's why the first part of the study. Of course, cosmetic formula are not simple aqueous solution, are not simple ethanolic solution. So we want to evaluate the performance of the model with much more cosmetic kind of vehicle. And for such purpose, we evaluate caffeine in 2 different emulsions. we evaluate water in whole, inverse emulsion and direct emulsion. Caffeine was solubilized in this formula at 0.5%. And we perform on these experiments, on these two different formula, a different set of experiments. And I will present some of them partially. For the formula characterization, we characterize the evaporation rate. And as you can see, depending on the type of formula, the inverse and the direct, the shape of the evaporation rate is different. And it reached ultimately a limit corresponding to the amount of water in the formula, which is the main component reflecting the volatility. We determine also the concentration in the saturation of the chemical in the aqueous. As for the other study, we performed the classical skin distribution. I don't want to insist so much on the results that I've already shown. Just one thing, there is no significant difference except for the stratum column between the two formula. We evaluate this classical ticket model as I reported here. I just want to insist on these parameters that we need to have partition and diffusion coefficient for stratum column, but also for the different skin layers. And we have three ways to have access to this partition and diffusion coefficient: calculated, measured through the skin distribution data that we obtain, or measured on isolated skin layers. The last point is about the dosage form. We evaluate two different options for the dosage form: emulsion or solvent. Here are the results for the caffeine in the inverse emulsion. And we also here compared different ways to implement the partition and diffusion coefficient. It's the skin distribution, the percentage in different skin layers, the percentage in dermal in the receptor field, and the kinetic in the receptor field. The blue correspond to the incremental value, and the three other bar graph correspond to the three different options for the partition coefficient. The first one corresponds to the calculated one, and is not really, it doesn't provide really relevant information. I just remind that the caffeine for the evaluation with the aqueous solution, the predicted TCAT value, the predicted partition diffusion coefficient was really appropriate. When we measured the partition diffusion coefficient, it is really not so effective. And we used the partition diffusion coefficient measure on isolated skin layers, which provide the best adequation with the experimental value. So for this type of formula, the measurement on isolated skin layers is much more appropriate, knowing that we still underestimate the amount in dermis. But it's not a general rules, because when we perform the same thing with the direct emulsion, none of the of this approach was appropriate. But another thing was that we have to consider it's the type of dosage form. So here in this plot, it corresponds to here you still have in blue the experimental value, or here in red the experimental value. This bar graph corresponds to the formulation when it's modelized as a cream, and these in dot correspond when the formulation is modelized as a solution. As you can see, for the inverse emulsion, the most appropriate is to simulate the formula as a cream, whereas for the direct emulsion, the most appropriate is to simulate the formula as a solution. That could make sense if you consider that the continuous phase of the direct emulsion is the water. So we can assume that for direct emulsion, maybe the most appropriate way is to characterize as a solution. So we can use TCAT model to simulate skin absorption. One of the things is that for the formula, we have to consider two parts in terms of optimization. First of all, we need to optimize we need to select the most appropriate dosage form. And the second thing, we need to select the most appropriate partition and diffusion coefficient. We assume that the formula affects the partition and diffusion coefficient of the stratum corneum, as it's directly in contact with the formula. And the partition and diffusion coefficient of the deeper skin layers, meaning epidermis and dermis, should be less affected by the formula. And the idea is to measure this partition and diffusion coefficient for epidermis and dermis in a different experiment, which is independent of the formula. Clearly, the future challenges are to define the formulation characteristic driving the skin absorption. So that's in such a way we expect that we are much more able to add the appropriate characteristic of the formula in the model. The second point is to design and validate standard protocol to measure this partition diffusion coefficient and to define the way to use this value with different PBPK models. The other main difficulty is that all models do not use the same kind of parameters. Have in mind that for the TCAT models, the partition and diffusion coefficient are normalized to water, whereas for other PBPK model, the partition coefficient are defined between continuous skin layers, meaning for the partition coefficient between epidermis and dermis is defined at the partition coefficient between epidermis and dermis for MSIF. But for TCAT, it's partition coefficient between water and epidermis, or partition coefficient between dermis and water. So that's all of the things that I can say on this topic. I realize that it's a little bit far away from the other presentation done today. I would like to thank many people involved in this study. I'm quite sure that the list is not complete. And all of this work was done with the support and with the expertise of the guys involved in this. And thank you for your attention.
Thank you very much, Sebastian. Unfortunately, there has been some problem with the audio, but I think most of the people got basically everything. So there are a few questions which I think partially has been answered by people in the chat, but maybe I can just quickly ask. So we lost your audio when you were talking about the epiderm model.
Yeah.
And why was it discarded, that one?
So it was epiderm wind. So the epiderm wind predicts what we mean by permeability coefficient. And the permeability coefficient is a kind of properties which is only focused on the amount in the what we name it's receptor fluid, meaning the amount in the blood circulation. Moreover, such kind of parameters is compliant when the experimental is done with infinite dose, meaning a large volume of vehicle applied on the skin. That's why the outcome of this model was not compliant with the experimental protocol we used. And also it was discarded for that reason.
Okay, thank you. And then there was a question from Jo Cook from Unilever, but she said that it was answered during your talk. Okay, so if there are no other questions, thank you again very much.